Okay, in this video we're going to analyze two-dimensional or projectile motion. And after completing this video, you should be able to set up a problem or problems so that they're ready to solve. You should be able to subscript variables so that they are easy for you and others to follow. You should be able to extract useful information from a description or situation and be aware that there may be many paths to a solution. We're going to tackle these objectives by looking at a situation which I have described here. A boy wants to try to his younger sister with a water balloon. He throws it at a speed of 15 meters per second from the roof of their 11-meter-high apartment building at an angle of 55 degrees above the horizontal. She is standing 25 feet from, let's make that meters, from the side of the building. Let's put her in the picture. First of all, let's cross that out and make that meters. We don't know where she is. He might hit her or he might not. So generically, at least, she could be here or she could be here or anywhere else in there. Now this 55 degrees above the horizontal, that phrase implies if we have a horizontal line and we draw a velocity vector, here's a velocity vector to indicate 15 meters per second at that 55 degrees. Okay, so that's 55 degrees above the horizontal. That's what that phrase means. All right. So in analyzing this situation, one of the first things that we want to do, or any situation, is to list the variables and place important points on the diagram. So let's go ahead and list those important points. We'll call that point A, we'll call the peak point B, and we'll call when it gets to the ground C. Now that's when it gets to the ground, not after it's been sitting there for a while. So in some sense, it has just gotten there, but has not slowed down yet. All right, after we've made those our trajectory, the path the object takes, and we've labeled important points, we can make a list of variables. And so that's the thing I'd like to do now. We're going to make a list of x variables, or those variables that apply to the horizontal motion of the ball, and we're going to make a list of y variables, those variables that apply to the rising and falling motion of the ball. And we're also going to make a list of other variables that apply to either dimension. All right, I'm going to get us started and then I'd like you to go ahead and see if you can fill in some other ones. All right, in the x dimension, we have things like delta x from A to C, delta x from A to B, and delta x from B to C. Now some of these we may know, some of them we may not, but again I want to make a list of all the possible variables. What else do we have? Well, we have the velocity at A, but we only want the x part of that velocity. So we're going to subscript like this to indicate the velocity at point A, but only the x component of that. Velocity at B, x. Velocity at C, x. Other variables that we have the x acceleration. Now in this case, the acceleration is constant all the way from A to C. It's in free fall. But in a case where that wouldn't be the case, you may have to further subscript your accelerations to indicate which segment. All right. So we have displacements, velocities, and acceleration. Now you come up with some of the variables on the y, the vertical side of things. Press pause, fill those in, and then you can come back and see what I have to say. All right, so we can do delta y from A to C. That is the displacement, vertical displacement from A to C. That is from here down to this level. We have delta y A to B and delta y from B to C. We have V AY, V BY. This is the rate at which it's moving upward initially at point B and the rate at which it's moving vertically at point C. Also, we have our vertical acceleration. Then in the other category, we have those variables that span between the x and the y, or act as a bridge. Things like the time interval from A to C, the time interval from A to B, and the time interval from B to C. By the way, if you would prefer just to use a notation like time from A to C, I prefer that too sometimes. It's just a little bit less to write. The other variable that spans across both dimensions is the variable theta, which is the angle. Okay. Let's take that as our list of variables. All right, now one of the objectives of this video is to get you to be able to see and figure out information from the problem. So let's start by taking a look at our list here and filling in those values that we can tell without doing any calculations. And I'm going to get us started. I think I'll switch my pen color for this. I'm going to get us started by saying that I know the acceleration in the vertical direction. I know that to be 9.8 meters per second per second. Now I'm not going to put a sign on it just yet because I haven't decided which is positive and negative. I think I'll go with what most people would say, which is this is negative and up is positive. But it doesn't have to be that way. And so in that case, the acceleration is downward, is negative. Now I want you to pause the video and try to fill in all the rest of these that you know. All right, here's another one. The roof, the displacement A to C, that's another thing that we know. It's right here, sort of. The displacement, the y displacement A to C is negative 11 meters. Negative because it's 11 meters down from where it started, and down is negative. All right, you pause it and see if you can find some of the other variables that we know without doing any calculations. All right, did you pick up on this? At the very peak of the ball's motion right there, the y component of its motion is 0. That is, at that point, it is temporarily not rising or falling. Now, if you picked up on delta x A to C, well, hold on a minute. We don't know that this water balloon hits her. All we know is that she's 25 feet from the building. We don't know if the balloon falls short, long, or actually hits her. So we don't actually know that. The other one we do know, however, is the x acceleration. And as you remember from your basketball activity, there is no acceleration in the horizontal direction. All right, those are the things that we know without any calculation. Oh, I guess we know this too. 55 degrees. So, at this point, we're pretty much ready to start solving. And we could ask many, many questions about this scenario here. In fact, why don't you put it on pause and see if you can write down 3 questions that we could ask of this scenario that we could answer using the physics that we know. All right, well, I'll let you answer those. What we're going to do is take a different approach, and that's to say, what if we didn't really know how to get to the answers to those questions? What could we do? This is a situation that any problem solver might eventually face is, I don't know how to solve the problem. One strategy, not a very efficient one, that you have is to actually find all the information possible, and certainly in that list of variables will be the answers to your questions. Now, I'm not suggesting you do this every time, but I am suggesting that if you get lost, finding all of these variables is a strategy to solve your problem. Let's go ahead and try to find some of these. The very first thing that I'm going to try to find, because it's fairly easy, is to find the x and y initial velocities. In some sense, what I really want to do right away is to break this motion into its 2 parts, the horizontal part and the vertical part. So I'm going to redraw my vector picture here. That's, oops, excuse me. that is 15 meters per second at an angle of 55 degrees. Now the x component is the length of the arrow if we do a perpendicular down there. This is VAX. And, switching colors, if we drop a perpendicular to the vertical axis, that is VAY. And again, that's a 90-degree angle in there. This is the speed at which it's rising, and that's the speed at which it's moving out horizontally. All right. Now you should notice that this is some trigonometry here. For example, we can find VAX by doing this. Cosine of the angle is equal to the adjacent side over the hypotenuse. Putting it in our terms, cosine 55 is equal to VAX over 15. And I'd like you to solve for that and then try to use your good trigonometry to find VAY. Did you find VAX is equal to 8.6? And did you find VAY is equal to, let's put these in here in green, VAX 8.6 meters per second. Could put units on all these. And did you find VAY was 12.2 meters per second? If you did your trigonometry right, or you might even be able to use the Pythagorean theorem, that's what you'd come up with. All right, I'm going to pause the video for a moment and start a new screen for us. Okay, so what other things can we find here? Well, you can find almost anything, but let's try to find the time from A to C. Let's make that our next goal. All right, so time from A to C. So this, we could think about trying to find it based on the y dimension or the x, because the time would apply to both. Notice how we have a lot of variables on the y side of things. That leads me to think that maybe that might be the easier approach. Well, we'll see. So I have, I'm not going to take a graphical approach. Instead, I'm going to take an algebraic approach. I have the definition of average velocity. I have the definition of acceleration. And I have our displacement formula. And all of these apply to both the x and y dimensions. Whoops, 1/2 AT squared. It's a plus sign. So let's imagine trying to find the time. I notice that it appears in each one of these equations. And I'm wondering, if I use this, then maybe I have to do a quadratic. And maybe I don't want to do that. So I come over here and I say, well, the problem is I don't know my velocity at point C. I do know it at A, so I won't be able to find my delta V from A to C in order to find delta T from A to C. So maybe I want to try this over here. I got the delta Y. I got some velocities. Maybe I can find the time. So I might try something like this. The average A to C is delta Y A to C over delta T A to C. And then I might come over here and start to put my variables in. But I look over here and I realize that even though I've got a 12.2, that isn't the average velocity from A to C. That's only the instantaneous velocity at point A. So I can't put that in there, and the subscripts show me that I've got two different variables. So in fact, I have two variables here that I don't know. Here, my only choice is to come back over here. So let's use the displacement equation, but let's use it properly in the y dimension. This is A to C, because I want to find the time from A to C. Velocity at A in the y dimension, plus the time, or times the time from A to C. That's what I decided I wanted to try to figure out. Plus 1/2 AY time from A to C squared. All right, now let's go ahead and put some numbers in. I think I'll go for work in blue. This is negative 11. I picked that up from right there. 12.2 t from A to C plus 1/2 times negative 9.8 times the time from A to C squared. Now that's a quadratic, so why don't you get out your quadratic solver and give that a go. All right, as you can see, when I did this in my quadratic solver, I either got negative 7/10 of a second or 3.2 seconds. Time can't be negative, so it must be the 3.2 seconds that we want. If you're curious, what this refers to is the amount of time, if it still had that acceleration coming backwards, that it would have started. So it would have taken sort of 0.7 seconds to get up to here if somebody had tossed it. But anyway, this is 3.2 seconds. And now we know that. What should we go for next? Well, some of you might realize that if the acceleration in the x is 0, that the velocity is constant. So we ought to be able to fill these in real quickly. And now our list is really filling up. Why don't you go ahead and try to calculate a few other things, realizing that the route there may not be a single equation. It may be a combination. It may be one equation and then another equation. And if you go ahead and spend 10 or 15 minutes doing that, I'll come back and give you the answers. Why don't you pause the video now? Okay, I'm going to show you how to calculate a few more of these things, and then I'll just put the answers up. We want to try to find the velocity at c in the vertical dimension. I can look up here and realize that that occurs in my acceleration definition. Not anywhere here and not here. That's an average, and that's a beginning. So a sub y should equal the velocity at c in the y dimension minus velocity, and I'm going to use back at a because that's what I know, but I could probably use some of the other, I could maybe use at b, and then this is going to be the time from a to c, which we just figured out. Let's put our variables in. Minus 9.8 equals velocity c at y, or velocity at c in the y dimension, minus y, minus 12.2, that is the velocity at a in the y dimension, divided by the time we just found from a to c, 3.2 seconds. And if you are clever with your calculator, you should get a velocity of 19.2 negative, because it's heading down at point C. This will be 19.2, but negative. Notice its velocity was positive to begin with because it was thrown up, but negative by the time it comes back down to the ground. All right. I'm now going to give you the answers to the rest of these, and you can check your work. Actually, let's do one more together. Let's do the time from A to B. Time from A to B. Okay, well, I'm looking at maybe, let's try using the acceleration. No, let's try using the average velocity equation. I want to show you something. Let's do the average velocity from A to B in the x direction. That will be the delta x from A to B. Oh, we don't know that. Okay, never mind. That won't work. Well, how about if we try the acceleration in the x direction? Okay, so let's see. We want the time from A to B. Okay, so let's do velocity bx minus velocity ax over delta t A to B. That should work. We know that, we know that, we know that. Let's see what that comes out to. Well, that's 0 equals 8.6 minus 8.6 over delta t from A to B. Ha! We've proved that 0 equals 0. Okay, it's a true statement, not very helpful, but it's true. That can happen. None of these equations will ever lead you astray. They may give you an answer that is not helpful, but it's not wrong. It just doesn't tell you anything like this. Instead, to find that time from A to B, let's use the y acceleration equation and go y, velocity B, y minus velocity A, y, over delta t A to B. This is negative 9.8. This is 0 minus 12.2 over time from A to B. And if you solve this, you should get delta t from A to B equaling 1.244 seconds. 1.24. Well, if that's the case, then A to C is pretty easy. That's just going to be 1.96. See if that adds up. 4 to make 2, 3, yeah. Okay, 1.96 seconds. All right, perhaps you will have finished the rest of these. Here are the answers. All right, there are all the answers. And hopefully if you've completed your work well, you came up with those. You may have taken a different path than I would have or than somebody else would have. But at this point now, I'm willing to bet that you could go ahead and answer any question that you came up about this. For example, does the water balloon hit the sister? How far from the side of the building did it land? How long was it in the air? How high did it ultimately get before it came back down? Any of those can be answered now that we have all of our variables found. So, while this is certainly a long approach, ultimately you can get where you might want to go. Eventually, though, of course, we hope you will find more direct paths to the problem that you want to solve. And that's the end of tonight's video.